the chat. I missed it. My bad. All right. Well, we're back in the game now, but I appreciate the reminder. Always, always. All right. So any value that falls outside of 2 standard deviations is going to be considered to be unusual. All right. So we have a mean of 72 and a standard deviation of 4. So we're going to compute x bar plus or minus 2s. So that's 72 plus or minus 2 times 4. All right. That in turn is 72 plus or minus 8, which gives you a lower bound, 72 minus 8, so 64, and an upper bound of 80. And so we put square brackets on this, on these two numbers. These are the usual suspects. So the usual values. You could also call it the ordinary values. All right. I don't know why I started this over so much. All right. Still haven't answered the question. It asked us to determine if 59 is unusual. Based on this information, I have to have values that are in between 64 and 80. 59 is not in between 64 and 80, so therefore 59 is considered to be unusual. So 59 is unusual because it is not between 64 and 80. Now, 64 and 80 inclusive, but it's already wordy enough. Inclusive as in if it were 64 or 80, it would still be a usual value. So 64 and 80 are still ordinary or usual values. It's anything less than 64 and anything more than 80 that would be considered unusual.
Professor, are the notes also on your page?
Yep.
All right, thanks.
No problem. All right, and so number 2, following data can be considered a simple random sample of ages of NFL players as of June 2019. And honestly, I don't even remember collecting this data, but I did. I must have, because this is definitely my my style of problem. Simple random sample, and we're going to do this in Unit 3 in more detail and more and with more emphasis on vocabulary and things like that. But a simple random sample is just saying that I took all the names of all the people that were in the NFL in the year 2019, put all their names in a hat, and then randomly selected whatever 20 values or whatever it is, 20 names, and then recorded the ages of the individuals I selected. All right. Since I don't remember doing this, I'm concerned that maybe I cheated and just kind of picked the players that I liked, but it's supposed to be without any kind of bias. So let me pause the. So we're going to determine outliers and unusual values based off of this data. So that means that we gotta, I think we want to get some technology involved here, because I don't want to find the mean and standard deviation. Well, the mean would have been fine. We just add them up and divide. But the standard deviation, I mean, this stuff, yeah, it was bad enough with 7 values. I'm going to have 20 values, and I'm going to have to figure out the standard deviation. That is a no thank you situation if I've ever seen one. So I'm going to use the Desmos calculator, and then later on I'll show you how you can use Google Sheets, because some of the graphs that we're going to work on, they kind of lend themselves to technology. I mean, they definitely lend themselves to technology. So Google Sheets has the functionality to be able to handle a lot of this stuff. I would normally say Excel, but I want the mobileness of Google Sheets to be a resource and an advantage for us. Excel, I know not everybody has it, not everybody has the same version of it. And even if you do, can you access it online? I mean, with the Office 365 account, you should be able to, but there's a learning curve involved in it. So I know Sheets is very like, open it up and get to work, you know? So that's kind of like where I'm at with my thinking there. But at this point, all I'm going to do is in my Desmos calculator, so just desmos.com, I'm going to hit that little plus sign, select table. It's one raw set of data. So I'm just going to start typing in these numbers. And once I do that, I'm going to let the calculator do the heavy lifting. I could organize it in a frequency table, but it isn't like there's so many values here that making a frequency table is going to save me too much time. And besides, we don't have or we're not using the kind of technology that would be able to efficiently handle frequency tables. So we're better off with the raw data anyway. I did a little research to try to figure out why a lot of these programs didn't have frequency table functions. And the best I can come up with is the fact that if you're using a calculator or a computer to evaluate data, you're probably doing it because the data is such a large set that just to organize it into a frequency table would take more time than than actually typing it in. So the better bet is to just work with the raw data. That's as far as an explanation, that's the best I can come up with. But in my mind, I feel like if they could do one, they should be able to do the other. But maybe I just don't know enough about programming. 1, 2, 3, 4. Just doing a quick double check because walking and chewing gum is not something I can handle on the best days. So me talking and typing in data is kind of along the same lines. So 4. Yeah, it looks good. So we need to determine the outliers and unusual values. So outliers has its own formula. Unusual values has its own formula. They all require us to make some computations. Now we're going to explain it in the context of the given situation. We're talking about the players' ages. So that's fine because even if you don't know what the NFL is or what is considered to be old or young in the NFL, you do know what a person's age is. So you can talk in general terms. So that's the one thing I always want you to be mindful of. Just because I'm using an example that talks about NFL players doesn't mean that you're going to be at a disadvantage to somebody who plays fantasy football regularly, you know, in answering questions. And in fact, I tend to stay away from, you know, specific problems like NFL and stuff like that on a test. I go to ones that are probably a little bit more accessible. Right. So I think it kind of makes sense if we're going to talk about outliers. I might want to write the formula for outliers. Right. So that's LQ minus 1.5 times the IQR, comma UQ plus 1.5 times the IQR. In brackets. Right. I'll also write the alternative form, you know, the technology variation of this, because, you know, the calculators tend to speak in terms of quartiles rather than lower and upper quartiles. So sometimes you see Q1 minus 1.5, and then this would be times the product of Q3 minus Q1. And then Q3 plus 1.5 times that same quantity. All right. It's a messier formula, but it has values that you can just pop right in, or at least it has places where you could pop values right in. So, there's schools of thought for both, and I've found people that say that the first formula is terrible and the second one is great, and I have just as many people saying the opposite is true. So, I give them both, and if you don't like either of them, I'll see if I can make up a new formula. I know there's other techniques that involve technology, so I can show that also. Right. So that's outliers, and then we have the unusual values. Whoa, that just skipped all over the place on me. I don't know why that happened. So the unusuals, so we just did that x bar plus or minus 2s. So the idea here is that we need information. We need Q1, Q3, x bar, and 2s. We come up with those pieces of information, we have everything we need, right? So at least to do the computation part of it. So what I'm going to do in my Desmos calculator is I'm going to select functions. All right, we have stats. We have all these different possible options here. One of them says mean. I need that. One of them says standard deviation. I need that too. Okay, so we're good there. So I can get that information right away. So the mean. Now, the mean of what? I don't want to retype all that data in. What I want is the column heading. That column heading is X1. So I'm going to type in X1. All right. You can close the parens or not. It doesn't make a difference. It already gave you the number, so we're good there. The mean is 31.25. So I'm just going to jot that down off on the side. I'm going to go purple for those keeping score at home. And I'm also going to get the standard deviation. So again, functions, standard deviation. One aspect of the Desmos calculator that I like more than some of the other ones is that it speaks kind of in ordinary terms. So it says mean instead of some like notation funkiness. It just flat out says the mean. And that's good. I like that. Right? And same thing with standard deviation. It doesn't say the full-blown thing, but it says enough for me to know that this is the thing I'm looking for. Also looking at X1. So X1. Right? So enter, locks it in case I need it later. And so I'm going to round this one to, well, normally I'd say 3 decimal places, but if I go 3 decimal places, I'm going to have 0.340. So I'm just going to say 6.34. All right, so I got that. I'm not actually going to do the computation for unusual just yet. I'm just collecting the information right now. So I need my quartiles. And then once I have my quartiles, then I'll do the number crunching, right? So back to functions. You see all of these different options here. Sometimes it's staring at you, like quartile function. And then sometimes it's sort of hidden. So you could use the quartile function, but then you could also go directly to stats. If you select the stats function, this one's the weird one because I type in X1. Sometimes it works, sometimes it doesn't. I don't know why. Sometimes you need squiggly brackets, sometimes you don't. All right, but if you ever get that orange triangle that shows up, that warning symbol, it just flat out tells you what you're missing. So if you accidentally type something, a syntax error, it'll correct you immediately. So that's good news. So enter. I need Q1 and Q3. So 27 and 34. So Q1 is equal to 27. Q3 is equal to 34. All right, so we got all that information. And if you think back to when we computed outliers the first time we were first learning about it, we spent a lot of time marking up the number set, the data set, finding the median, and then the median again, and showing all the computations. Now it's like, let's cut to the chase here. You know, so that's really kind of where I'm at with it. And I encourage you to be that way also. Right. So I'm just going to jot it at the bottom here. So 27 minus 1.5 times Q3 minus Q1. I could just chuck that over here. Q3 minus Q1. That's equal to 7. So that'll help me come up with my lower bound, comma, my upper bound is Q3, which is the 34, plus 1.5 times that 7 again. All right, so we just got to crunch these numbers, and then we'll have the interval for which, or we'll find the interval of non-outliers. And so from that, we'll be able to make a determination of what are outliers and what aren't. All right, so let me get a red. Nah, I'm going to go blue for those keeping score on. So 27, it's really 27 minus 10 and a half, but I'll just jot it in here. So 27 minus 1.5 times 7, so 16.5. So that's the lower bound. And then on the upper bound, we're talking about 34 plus 1.5 times 7. So 44 and a half. Right. So that gives me the interval of values that are not outliers. Just bring that in a little bit, a little easier to see. All right. So any value that falls in between 16 and a half and 44 and a half would not be an outlier. So we look at our data. Well, this is the part of it where maybe knowing a little bit about the NFL could be helpful, because I don't think anybody who is familiar with the NFL would expect there to be a 16-year-old or younger player. Right. So if I told you a player is 15 years old, you'd be like, no, that's not happening. They'd get killed on their first day. Right. Now, so that we don't have any outliers on the low end, but on the high side, 44 actually makes the cut. So that's not an outlier, but 46 is an outlier. All right, and we'll explain what it means in the context of the situation in a few minutes. But for now, all we're getting at here is the idea that that's a value that's so absurdly different from everything else that it really shouldn't be there. So now we start getting into, okay, well, why is it there? So that was my HGH joke. You know, like how can a 46-year-old be playing football still? But then you find out he's a kicker. You're like, oh, all right, well, they don't get hit. You know, less risk of injury. So we're looking at somebody who's probably, you know, if he ever got injured, it was probably self-inflicted, you know. So that gives you a little bit of a sense, hopefully. Now, in terms of the unusual values, because what we do is we tend to think of outliers as just a more extreme form of unusualness, right? So we have unusual values, and we talk about things being unusual all the time. Oh, that's unusual. I didn't expect that to happen. That's weird. You know, that's different. You know, we use different kind of language to describe it, but it all talking about the same thing. It's just some sort of occurrence that you didn't expect to happen. All right. But you're not saying it's impossible. Like, whoa, I didn't see that coming. Not like, no, that can't be right. Right. So it's like like a quick example would be if you've got, let's say you worked a lot of overtime and you got your paycheck and it's like double the amount that it normally is. You're like, whoa, all right, how you doing? Double the amount. That's great. Didn't see that coming. I know I worked a lot extra, but I didn't double. Wow, it's wonderful. pleasant surprise, as opposed to like getting a paycheck for like $1.5 million. You're like, ooh, might have to give some of this back. That's a mistake, you know? So one is like, I didn't see that coming. The other is like, this can't be right, right? So we just figured out the interval that allows us to determine what just can't be right, right? That 46 just can't be right. There's got to be an explanation for that. Unusual, it's like, okay, well, these are some extreme values. I mean, in baseball, Major League Baseball, you could have players as young as 18, 19 years old playing. So like you can see some youngish players. Whereas in football, you tend not to because of the development aspect of it, right? Physical development. Anyway, this is telling me to take 31.25, add to it and subtract from it 2 times 6.34. Right, so it's relatively simple computation. I like to, previously I did it separately because the numbers are nice, but I like to kind of get it done all in one shot. So minus 2 times 6.34. And then just do the same thing again, but with a plus sign. 31.25 plus 2 times 6.34. So I got my two bounds. So on the low side, we got 18.57. On the high side, 43.93. All right, so these are the usual values. So now I just reflect back on the data set and I see what value or values really just don't make the cut, right? So it's still on the high side because there's no value in this data set that's near 18, but I do see now that 44 would be considered on the unusually high side, right? So I'm going to circle this. These are my unusual values, which starts with an un. All right, so then it's just a question of,
I have a quick question. So for 43.93, why did you not round up for that 44? Why'd you only keep it at 43.93? Because then if realistically, if it is 43.9, it could still be 44.
Yeah, so I had a choice in the matter, and I kind of went with the data.
Okay.
And I kind of sort of, and that's where statistics can be a little fuzzy and manipulative, because I wanted 44 to be unusual, and by rounding it this way, it made it happen. So if you have a motivation behind any situation, rounding could be an effective tool to help you kind of fudge the numbers. So legally though, so round this to 44, and all of a sudden that number 44 is not unusual. So depending on what the rationale is for that could be like a meaningful form of trickery. So, but in this case, we're talking about context. We're talking about age. So, regardless of NFL, it could be NFL, it could be hockey, it could be teachers' ages, it could be anything. So we just want to describe what this means, right? So 46. I'm just going to make that blue. 46 is an outlier, meaning it is so extreme that its presence requires an explanation. All right. Now that's not the contextual explanation. I'm actually going to shrink some of this down. If anybody's looking for typo bonus, more room for number 2. Most of you, I think, are doing this on notebook paper. I don't even know that for a fact. You just be making that up. But if you're doing it on the handout, there's definitely not enough room. So that's getting at what an outlier is. And so extreme that its presence requires an explanation. So in this case, now we didn't associate names with numbers here. So we're talking like in general terms, but we can make a reasonable assumption that this is a player who avoided injury over a long period of time. I'm trying to keep it in simple terms because I know not everybody is really knowledgeable about football, American football, and even if they were, it doesn't mean that it's a topic of interest. So just trying to speak in general terms, but basically what this means is if a player in a violent sport is able to continue playing in that violent sport to the age of 46, then he must not have gotten hurt. So it actually asks more questions than it answers. So I would be looking at why. Why is that the case? So I'll put a little Y at the end with a question mark, because it's my way of saying that it requires a little further investigation. Like I would want to know who the player was, and if he is a position player, like a running back or someone who takes a lot of hits, then I would want to know like what their secret is. How can they still be in the league at that age, right? So next, the unusual values. 44 and 46 are unusual because they deviate by more than 2 standard deviations from the mean. All right, so that's, like I was saying before, for outliers, that's telling me what an unusual value is. It's not addressing it in the context of the situation. All right, so again, we're talking about ages of individuals. So are we talking about injuries here? Are we talking about position players? Or are we just talking about players who just don't know when to quit? All right, so they're unusual because they deviate by more than 2 standard deviations away from the mean. But this could be avoidance of injury, all right? They may not be starting players. They could be in a backup role. So backup players. All right, so for those of you who don't know, in most sports, you have like the starting line players. Those are the better players, and if they get hurt or they get tired, then you rotate them out and you put in their backups. If you're familiar with like Broadway shows and stuff like that, it would be the equivalent of an understudy, right? So avoidance of injury, backup players, or maybe just don't know when to quit. Right? So overstayed their welcome. All right. So as for an explanation when it comes to an assessment, because like this is all fun and games when it's academic, but when push comes to shove, like you're going to have a problem on a test that you're going to have to answer. And some of you right now are like, well, please don't let it be football, and I'm fine. But then what if it's vehicle emissions? What if it's population growth over time? Like it's going to be some contextual situation, and you're going to have to evaluate, the consequences of the statistics. Does it make sense, and what did we learn from it, right? So what I'm saying here, and really this is more like a brainstorming kind of thing, because I didn't really draw any kind of meaningful conclusion other than to say, well, there's got to be an explanation, and here are some possibilities. And so as long as you do something along those lines, you're going to be perfectly fine. Right? So if you were to say 46 is an outlier because I'm just thinking, I remember my mind always takes me to sports. There is a player for the Mets a long time ago. He was good, and then he was terrible. Tom Glavine. So he was an Atlanta Brave, and then he became a Met, and then he started to be terrible after that because he became a Met. But anyway, towards the end of his career, apparently his brother was a minor league player, so he wasn't in a major league club. And so because he was a famous athlete, he was able to pull some strings to get his older brother onto the team. Basically saying, do me a favor, bring up my brother and let him be a major league baseball player for a little while. He wasn't good enough to do it on his own, but his younger brother was a Hall of Fame pitcher. So he was like, you know what, I can get my brother on here. So like that kind of circumstance could be the reason why you have a 46-year-old, playing in a league. That's not the reason for this case, but it could be some extraordinary circumstance where it's like, hey, I'm LeBron James, so I'm the best player in all of basketball, all over the world. I have a friend who also wants to play basketball, and so you're just gonna put him on the team. Why? Because they said so, and you want to make me happy. Sometimes it's like that. Not to say that LeBron James ever did that, but I'm pretty sure. I'm forgetting which NBA player did that, but it was pretty recent. It was somebody who was. It doesn't matter. I'll look it up and we'll bring it up at the worst possible time. But that's an example. That could be how an outlier comes into play. Something extraordinary like that. Are you going to guess that when you see a data set on a test? Probably not, but that might be the reason. So what you do is you just put what you think might be a reasonable explanation for why there's an outlier, and then you're good to go. All right. So let me stop this recording.